In this video, we'll take a look at the House of Einherjar heap exploit for glibc 227. So the House of Einherjar is essentially a heap exploit that takes advantage of a bug where you have a single null-byte overflow in a chunk, and we'll see what the implications of that are. So I created a small binary that implements a note keeper, and essentially you can allocate a new note, and when you allocate, you have the option of initializing the data that goes in that note. You can also edit the data of an existing chunk. We can print a note, and we can also delete an existing note. So the problems with this binary, which has everything else implemented correctly, like during the delete, we properly zero out, we clear the reference to the pointer in memory so it can't be used after free. So we don't have those kinds of problems, but we do have a couple of vulnerabilities here. The first is not so much vulnerability, just a way that makes the attack a little bit easier. In allocate here, we have the option of not forcing chunks to be initialized. And we know this is a problem because glibc, when it allocates chunks with malloc, it doesn't initialize the data there. So whatever data is there, including potential pointers and so forth, will be retained if we don't choose to initialize the chunk. And the real vulnerability with this binary is that there is a single null-byte overflow in the right chunk subroutine, which is actually called by the allocate function here and also the edit function. So the issue here is that we are using fgets. So fgets by itself is good because it allows us to limit the size of the input that we read. But if we look at the man page for fgets, actually it shows that it reads at most one less than the size, and then it makes sure that it's the string is null terminated. So the problem here is that when we're using fgets, we shouldn't add 1 to the size of the string that we're reading, because fgets kind of internally manages the fact that the string will be null terminated. If we add 1, then essentially that no longer guarantees that the string will be at most size bytes. The string will be, in this case, at most size plus 1, where the last index will be a null byte. So this is an issue. But it's only a single null byte, right? That's only 1 byte of overflow, and furthermore, we can't even control what the overflow value is. So this seems this doesn't seem like it will yield any potential attack surfaces, but actually it does, because recall that in glibc, the structure of a chunk is such that the some metadata about the previous chunk is stored in the size field, right? For example, there's a prev in use bit. Actually, that's the lowest bit of the chunk size. That basically indicates whether or not the previous chunk is freed. By freed, I mean fully freed. In other words, Tcache, of course, doesn't really count, because in Tcache, we don't truly free the chunk. It's just sort of managed in the heap itself, so it's not technically free, and it is technically in use. But by overflowing the single null byte, we essentially do two things. We first clear that in-use bit, which means that the previous chunk appears to the heap allocator to be no longer in use. And this is important because now it can be unlinked from unlinked from a bin and then consolidated with the current chunk. And we can also use it to change the size of the previous chunk. But because we can only write null-byte, we can only essentially write we can only change the size to be the highest multiple of 256 below the encrypted value. And if we have a chunk that is, say, less than 100, say like hex F0, then this overflow will actually mess up the program because we cannot have a chunk that is 0 bytes in size. So to see how this attack works, let's start with our heap layout. Of course, we can allocate these chunks here. We have sizes of 100 for each of these cases, and both of the prev and use bits are set. So if we write the data for this first chunk, because we have the null-byte overflow, we're able to essentially write into this least significant bit of the size field of the next chunk. So this gives us actually hex 100 here, which tricks the allocator into thinking that this whatever chunk comes immediately before the second chunk is actually free. So because we have control over all of the data in the first chunk here, we can make a fake chunk here that say is of size 80, and we can of course control all of this data. So we can first write a size field here, making sure to set the previous chunk to be in use so we don't further consolidate. And here we can set the forward and backward pointer of this fake chunk to the chunk itself. And this is nice because this will actually bypass the forward backward checks when we in the unlink macro. And then the prev and use, or the previous size, can be set to 80 to denote that that's the size of this current chunk. So this is the code from glibc. And if we take a look at the unlink macro, first we can see that there are a couple of checks that we have to bypass. The first is that the size fields has to match with each other. So in order to accomplish that, we essentially make sure that whatever is in this field here agrees with where this chunk is at in memory and where this hex 81 is situated. But this is easy enough to do because we essentially have the position of this, the relative position of these two fields in the heap. The second thing that has to be satisfied is that the back pointer of the forward entry, the forward node, has to equal the node itself, and the same thing with the forward pointer of the backward node. So what does this in a freed chunk, right? We have two pointers, the forward and the backward pointer. The forward pointer points to the next chunk that's in the linked list. So we have to make sure that whatever is next in the linked list has a backward pointer that is equal to this chunk, right? The forward chunk has to be pointing to this current chunk. And the same thing with the previous one. The next pointer of the previous chunk has to be equal to the current chunk. And by basically writing the address of the chunk in both of these fields, we satisfy both conditions, right? Because if we, for example, if we consider the first check here, the back pointer of the forward one. So first we are going to take a look at this. Whatever is here is L, so we go to L, and then we look at the back pointer, and that's indeed pointing to L, right? So that actually is satisfied. And then this same thing with the backward pointer. If we go to L first and then look at the forward pointer, it's still L. Essentially what we have here is a chunk that points to itself. It's a linked list that's linked to itself infinitely, which is okay. It bypasses the checks, so we're good. And then after the forward and backward link pointers are checked, then we essentially unlink this chunk. So what that means is we would take the backward pointer and write it to the forward pointer of the backward pointer of the forward chunk, and we write the forward pointer to the forward pointer of the backward chunk. But because everything points to itself, nothing's going to happen, right? We're just going to we're unlinking this chunk that points to itself, so it's still going to end up like exactly like it is. But the important thing here is that after we unlink this chunk, we can now consolidate it. We consolidate backwards. So this forward chunk here, that's 100. Whenever we free this chunk, it will be consolidated backwards to merge with this fake chunk that we created. So what that looks like here is, so say in one case we would have that there is a chunk that's in use after the second chunk here. So here I just put the smallest chunk size hex 21. What happens in this case is that whenever we free the second chunk, it will be consolidated with this hex 81. So now we'll have essentially this huge chunk that's hex 181, right? And it actually overlaps with our first chunk that we used to write, basically create the fake chunk. So now we have two overlapping chunks in this case. And note that this hex 21 becomes hex 20, and we also have hex 180 written here because now this chunk here is basically freed, right? It was consolidated. Another situation happens if the third chunk, the chunk following the second chunk here, is the top chunk. In other words, we have this hex 100, and then the large chunk at the end. And what happens here is that we still have a similar thing. The top chunk actually the chunk here gets consolidated forward. So these two together get consolidated into the top chunk. And now we have this huge top chunk that still overlaps with the first chunk here. So in either case, we have overlapping chunks that overlaps with the first chunk in this region. So to basically, now that we have overlapping chunks, we can easily exploit the program because assuming we have the leaks to libc, and we can simply allocate a chunk, free it, and then modify its pointers, right? Because essentially we can control all the heap metadata that belongs to the second chunk. So in 227, we can poison the Tcache and get an arbitrary write at free hook to write system, which is very simple. So how this would work is first we'd free X to the Tcache, right? But make sure X is allocated from this overlap region. For example, it can be here. And then after X is freed, we can now modify the first chunk's data again, right? To basically overwrite the contents of X. And then after that, when we allocate X, we'll poison the Tcache because whatever we wrote to the forward pointer will be now next in line in the Tcache. And in 227, actually, there's no checks on this, how many chunks are in the Tcache, which is actually kind of bad, right? Because as long as the next pointer is not null, then the allocator thinks that there's still more data in the Tcache. So if we write free hook to this freed Tcache chunk, and then we allocate, then the Tcache will now have the free hook here, and then if we allocate again, we're going to get a chunk that's situated at the free hook. And then there we can just write system, and then we can free a chunk that has bin sh in it to get the shell. And of course, we need to get leaks. And what leaks do we need? Well, because we need to first create this fake chunk that satisfies the forward and backwards checks, we have to leak the heap. which is actually very easy because we can just find the Tcache by freeing two chunks in quick order, and then reading the information. And then we also need the address of libc so that we can get the free hook and system addresses. And to do that is slightly harder, but it's still very manageable. So first we want to free a non-fast bin, small bin chunk to the unsorted bin. In fact, the chunk doesn't have to be small necessarily, but it works just as well with the small chunk. And to do this, we need to make sure that we first, of course, fill up the Tcache corresponding to the size, and then that way the next free will overflow right into the unsorted bin. And after we have the chunk free to the unsorted bin, we can now request a slightly smaller chunk, a chunk of size hex 10 less than the previous chunk. And this is nice because what will happen is the allocator will see that the size is not exactly equal. So it will first bin the unsorted bin, the chunk here, into the correct small bin. And then it will search through the small bin and return us the chunk itself, because there is no chunk size. We can't essentially carve anything from the larger chunk because hex 10 is not enough to have metadata plus actual data. So it will just get the entire chunk, even though we request something that's actually less than the size of that first chunk. And this makes sure that the heap is aligned properly, everything is nice, but more importantly, it won't go to Tcache first. So the small bin address will still be located in the corresponding field of that free chunk. And this allows us to get a libc leak because the small bin is in the main arena of libc. There is an issue with requesting the same size as I mentioned, and the issue here is that if we look at the code in libc, we can see that if the size is exactly equal to the requested size, then what happens is we first fill the Tcache, basically copy the chunks over. And this is a problem because when we do that, the Tcache will either write it with the 0, or if there's already things in the Tcache, then it will write it with the heap address. But this will basically overwrite the libc small bin address that we wanted to leak in the first place. And again, this can be avoided just by requesting just a slightly smaller chunk. That way we force the binning and then prevent first stashing to the Tcache. So to kind of demonstrate the attack, what I have here is the exploit for this challenge. So if you're trying to exploit this on your own, and try not to look too much happening here, but just to show what's happening, we're going to look at the state of the heap right after we perform this overwrite here. So let's go ahead and run this. So okay, and we have to first fix this thing. All right. So we're going to break that address plus FEB. And if we continue, we now look at the chunks that are in our program, and then more importantly, we're going to take a look at a bunch of data on the heap here. So let's look at what the heap looks like just before we perform this malicious overwrite. So we can see here that this is the actual chunk here, and we've overwritten the least significant byte of the next chunk here with a null-byte, right? Because we basically wrote everything here. And f gets terminated the string with the null-byte, even though it technically didn't need to because we input null-bytes. But anyway, we can see that just by looking at this, we kind of created a very convincing fake chunk here that has the previous size here set to 80, and we have the chunk header here at 80. And we set the previous in use bit of this 80 chunk to 1, just to denote that this stuff here is still in use. So if we look at the pointers here, we can see that both of the forward and backward pointer points to the chunk itself, and this was because we had a heap leak, so we could calculate these addresses. And so when we now free this chunk here, which is actually bordering the top chunk, what will happen first is it will consolidate with this free chunk here, and then both of those will get consolidated with the top chunk. So now we'll have a top chunk starting here. That will be hex 180 larger than what it is currently is. So now to demonstrate that this actually happens, go ahead and look at what happens after we free that second chunk and get that consolidation. So we're going to again continue here. And now look at our heap. Okay. So the addresses should be a little bit different. Maybe they're not because I'm debugging. But what we can see now is that this is the chunk. This is now the top chunk. And we actually see the remnants of our original top chunk here, as well as the stuff from our fake chunk here. So we can still see that previous size. So kind of compare that with what we saw here. And we can see that, yeah, the prev in use bit of this top chunk is, of course, set. And we have still these two pointers. These pointers are kind of useless now. glibc doesn't care about them because this is the top chunk. So these pointers still point to here, but it doesn't really mean anything. And yeah, so essentially we have a new top. And now whenever we allocate a new chunk, we're going to get it from the top. So we're going to overlap with this chunk. So let's look at that quickly. Okay, so now we're going to put a breakpoint here. And what's going to happen is after we get the overlapping chunks, we're going to allocate, which will be allocated from the overlap chunk. We're going to delete it, and then we're going to modify it to point to free hook. So let's take a look at that. Maybe we have to try again. Sometimes it doesn't always work. Right, now we can 32. Okay. Now we can see the new top is here, but we allocated this small chunk here. And we can see that by overriding this chunk, by writing the data, this is legitimate data for this chunk, we have overwritten the next pointer for this freed chunk. So to show this, we can first find this chunk to see if it's pointing to, and we can see that indeed the heap is pointing to this chunk. The heap is pointing to this, and now that we've set the next pointer, right after this one is freed, then this one will be the next to be allocated. And so essentially at that point we have already poisoned the Tcache, and then we can just get a shell from there. So if we see that in action now, continue, and we can see that we get a new program, bin dash. Okay. And we can see, of course, that the shell is running. And even when we exit, we get a clean exit from the shell. We're still back in the program. And of course, we can exit again. Okay, so that is House of Einherjar. Essentially, it's a single null-byte overflow that can be used to trick the allocator into thinking that the previous chunk is free when it's actually not, or when it's actually a fake chunk. And then from this consolidation, we can get two overlapping chunks, which then we can use, of course, to control metadata and poison Tcache or perform any other arbitrary writes that we need to finish the exploit. Okay, thanks for watching.